Well, welcome back once again. We're about ready to finish off our 13th week of the entire semester. And congratulations on getting through the third exam. The fun fact about this one is that for this course, we're going to have a take-home final exam, which is like a glorified long homework assignment. And so this was our last in-person exam. I'll start grading our third exam after getting caught up with all the grading. Assignment 10 is going to be due on today, it turns out. So once I get caught up on all grading, I'll turn over to grading exam 3, and I'll have all the grades and feedback posted in this portion here. Well, that's where we're at so far. And with this point to where we're at in the course right now, we're pretty much in the wrap-up phase. Looking into the calendar, on the 20th, we're going into week 14. 27th is the last instructional week, week 15, and final exam week starts on Monday, May 4th. So what we're going to do on this final week here, week number 15, is finish up whatever topic we were working on, possibly the ANOVA method on the 27th, and then immediately transition into reviewing for the whole course. We will review again on the 29th. Then at the very end of that review, probably about 15 minutes before class ends, 2 weeks from today on the 29th, I'll unlock the final exam. We'll look it over as a class, briefly discuss it, and then the final exam is going to be considered assigned on Wednesday. It'll be due over finals week with a final due date on the 8th of May. But that's kind of the nice thing about this course. I've always debated if we should do a project or a final exam like a take-home final exam. So that's kind of what the take-home final exam is sort of all about, kind of like an extended project, a type of hybrid homework exercise where you get to practice doing complete analyses of data in random scenarios. So the major tool we're going to be working with and discussing more and more as we get towards that last day of class is this table right here. This explains really what chapter 1 was all about when we were discussing what is a quantitative variable, what is a categorical variable, how to tell them apart. The whole purpose of that is if you know what the variables are in your study, and we're going to put in another block here to end the course, you'll know exactly what statistical procedure you're really running. And I put here what chapter to look up to find the specifics on writing out hypotheses, looking up the R syntax, anything along those lines, checking conditions, and so on. So we'll be coming back to this table, but at the moment it's kind of like a big cheat sheet for determining if you have a random statistical problem, and you're not sure what chapter you're in, consider the variables, and this will tell you exactly how to proceed. Well, that's where we're at so far. We're working through chapter 21. We're going to extend the chi-squared methods into chapter 22. But any questions or comments at all, folks, before we get started today? Okay, well, we have a really pretty good idea at this point of the course on what statistics are. So the major thing that gets tricky, now that we have a lot of actual statistical methods, is choosing that method. So right now in chapter 21, the reason we're using the chi-squared procedure is because we have exactly one categorical variable. But the issue is we can't classify the outcomes of this variable as successes and failures any longer because there's 3 outcomes, or 4, 5, 6, and so on. If there's strictly more than 2 outcomes to that categorical variable, that's when we use the chi-square test for goodness of fit. But then chapter 22 is interesting. Chi-squared comes up again. And these are both pretty small chapters. The author could have put them together. It would have been about as long as chapter 20, really. But the reason the author made a good call to keep them apart is the variables are actually different in chapter 22. The idea of chapter 22 is it's not one categorical variable, there's exactly 2 now. And at least one of those variables, I'm going to reword that. What this is trying to say in the parenthetical is that at least one of those 2 categorical variables has more than 2 outcomes, which means doesn't fit in the chapter 20 procedure whatsoever. One of those variables, or maybe both of them, having 3 outcomes or more, means we're using the chi-square test once again for 2-way tables. So we'll see how that goes, possibly today, depending on the pacing of the day, as well as certainly on Monday, probably finishing on Monday at the latest. So that's where we are at, where we're going. Our last method for the entire course is going to be analysis of variance. So once again, we'll extend this table further, explain why you would ever choose analysis of variance, and then cite this table quite heavily as we're doing our review for the course. So here's where we left off. We made a good call to not rush on our Thursday a week ago from today, or Wednesday a week ago from today. Pretty much what we did is we just analyzed the context, defined what the parameters were, and we're about to state what the null alternative hypotheses are. So let's refresh on what this was all about. The recap is, this is about the classification of violent crime, specifically homicides in one particular city or metropolitan area. This data was published in 1988, but it could have been a longer term observational study when they gathered all these data. We have classified 1361 observations. They're specifically homicides according to one categorical variable with the outcomes of what season did it specifically fall under: winter, spring, summer, and fall. And one natural question when we look at these data is, notice there's a slight bump in summer. Slightly more people or incidences of homicide occurred in that particular season. That's what we want to know. Is there a relationship between incidents of homicide and the particular season that they occurred in for this one area? So we pretty much rephrased it here in the statement phase. And now that we have 4 outcomes, when we go to write our parameters, we're matching a parameter for every single one of those outcomes. So we let P1 through P4 denote the true proportion of all homicides in this area that occur according to one of these 4 seasons, winter through fall, respectively. With that all on paper, we're ready to start stating the hypotheses. And that's a pretty good screenshot we have down below here. Let's cite that for the next step. Any questions at all, folks, with the recap? Okay, well, the reading for this in the textbook is tricky because our author gives this general null hypothesis structure. We're going to use that in the very next example to show how it goes, but not all problems fit naturally in this way. We could make it work. Say P1 is equal to 1/4, P2 is 1/4, through P4 is 1/4. The reason we might go that way is the null hypothesis is a statement that nothing is really going on in the population. There's no interesting effect. And that kind of statement would say there's an equally likely chance of a homicide occurring in any one of these particular seasons. But if you have an equal likely chance for all these values, we usually write it in this term. Our null hypothesis is just going to say P1 through P4 are all equal. So let's write it out in this format. We can say let H naught be the statement that nothing particular interesting is happening with the relationship between homicide and seasons they occur in, which means the proportion of homicides, P1, will be equal to P2, which will be equal to P3, which will be equal to P4. Since these are equal lengths of time dividing up the years, that's a natural way to break up the proportions. If they're all equal to each other, well, they also have to all add up to 1, like we wrote here in green. That means we can write P naught is equal to 1 over, it says K, the number of outcomes. K is 4 in our problem, or just match up that 4 you see there in the subscript. We're saying all of them equals exactly 1/4, or 0.25 if you prefer. So that's our null we're going to test. Nothing's happening in the population. These are just random, and it was just by random luck there's a blip on summer. The alternative hypothesis is going to say that's not true. There's at least something going on here in this data. Not only is this count high, but those other 2 counts, winter and fall, are kind of low because this one's high. So the alternative hypothesis goes this way. We'll let H naught be that, and HA be the statement that, let me see if I put that in the screenshot. Looks like I didn't. Let me cite something different. There we go. HA is going to be the statement that PI is not equal to PI naught. Well, the PI naught is the 1/4. It's the same value that gets put into every one of these parameters. They're all equal to 1/4. So we're saying at least one of these proportions, PI, is not equal to PI naught from the null hypothesis. For some I, or at least one I is one way to say it. So carrying down paper, we could say PI is not equal to 1/4. So this value we see here is PI naught in the statement of the formulas, all of them set equal to 1/4. PI is not equal to 1/4. We absolutely have to say at least a little bit more. Say at least for some I, or say at least one I is another equivalent way to say it. So complete the statement by saying for some, I'll be a little bit more specific, I equals 1, 2, 3, or 4, using comma to say or. So essentially what we're saying is negating the statement fully. When we say for some I through 1 through 4, we're meaning either the first equation is false, P1 is not a fourth, or the second equation is false, P2 is not a fourth, and so on. But it also includes a possibility that maybe two equations are false at the same time, any pair, or the possibility that three equations are false. And in addition to that, a fourth possibility that they're just all false equations. Every one of these values should be different than a fourth. So this is a really big statement. It includes all possibilities. When you negate the statement that they're all equal, lots of different things could actually happen. Because there's so much going on with this one, sometimes this is called an overall test. We're making an overall test for any difference whatsoever in our alternative hypothesis. So there they are. That's the kind of the trickiest thing about chi-squared procedures, is stating the null and alternative. Parameters are very similar to what we did before, but our hypotheses are starting to look really, really different, and they'll get even more different in the next chapter. Well, we need a significance level alpha. The problem didn't provide one. So let's go for maybe, let's say anyone has a really strong opinion on a different direction on alpha. Let's say test at alpha equals 0.01. I think the claim is pretty bold to say there is one particular season where the incidence of homicide is higher. If there's any certain season that occurs, maybe summer, because more people are out amongst each other. So maybe that could really be an effect here. But I would say I would want a lot of evidence in order to say we have statistically significant evidence for an effect like that. So personally, I would set alpha to 0.01. Some problems will say what to test at in their write-up, but occasionally in homework problems and in the final exam problems, you might have to come up with your own, like we did here. So we have the full statement of hypotheses. What we're doing next in the notes is just looking at the overall procedure so at this point. Any questions or comments at this stage? Okay, before we do the math side, all the computations, we're going to take a look into the conditions. Conditions are not too bad for chi-squared. For homework questions and final exam questions, these are the major two conditions we're going to look into. Well, there's really three, but I've got them blocked into two spots. First thing is we want to know if we have a random sample. So we'll say whatever the problem tells us or fails to tell us. And looking through this again, it just said it classified 1,361 homicides. So this is a common situation we found ourselves in. There's no information on whether or not this is random. You could learn more by looking up the study, but you never have to do that for this course, only if you're really interested in it. So we'll go based off the short write-up on example 1 and say, for part 1 of condition checking, it is not known if the sample is random. So part 1's done. Now part 2, we have these particular counts that came up in the study. And depending on what the null hypothesis looks like, a random sample of 1361 observations, that might not be enough. That sample might be too small, especially if we said one of these parameters takes on a very, very small proportion. We could be in slight trouble there. So here's what we have to check specifically. Sorry, wrong tab there. We need to check that no more than 20% of the expected counts come out less than 5. And all expected counts have to be at minimum a 1, which means pretty much all we're doing for the second wave of the conditions are just compute the expected counts. Here's the formula. It's kind of nice. It's just n times pi naught. Let's throw this into our document as just a temporary screenshot to consider that as we work through it. Trickiest thing about this is, what is pi naught? In some hypotheses, it's different for every value of I, 1 through 4, or maybe it's 1 through 10, and so on. But for ours, pi naught is 1/4 on every single value. So the expected counts is just take your total sample size n, multiply by the value in our null hypothesis, 0.25. So that's a really fast computation. Let's put here the expected counts. Might as well match up the color coding. Let's go with green. For the next conditions, 2 and 3, the expected counts are n times pi naught. N is the overall sample size, 1,361 individuals, multiplied by pi naught is 1/4. And this is the same expected count for every single category, winter through fall. It'll be a little bit different in the next problem because we'll have different probabilities for every parameter. But for this problem, not so bad. Let's just go 1361 times 1/4. And we don't round on this. The idea is if we repeat this study over and over again, taking different simple random samples at the exact same sample size, 1361 every time, then on average, if the null hypothesis is really true, this is how many successes we expect. 340.25 is important here for every one of the categories, winter through fall. Our actual successes, or excuse me, expected counts, not successes, our actual counts were 328, 334, 372, 327. And it's saying if the null hypothesis is true, they should be close to that. It's saying it's only above or below just by random sampling alone is the only effect there. But this one's a large actual count versus the expected count. So if we reject the null hypothesis, it's going to have a lot to do with what happened in summer. But let's put down on paper, the expected count is 340.25. Let me double check that value again. For all categories. The categories being the 4 seasons. So we had to check that all expected successes are at least 1, no more than 20% is below 5. So if this had, say, only 2 expected successes, then the whole condition would fail. Sample size wouldn't have been large enough. But this is really, really large. Actually, let me put here just as a quick reminder on the condition, it's greater than or equal to 5 for all categories. And so this tells us that conditions 2 and 3 are met. The sample size is large enough. So the only unknown about these conditions at the moment is not known if the sample itself was a random sample. We got it, folks. That's doing the expected counts. It's pretty fast for this kind of situation where there's only one pi naught value whatsoever. Just multiply against the sample size, and that's the same count for every single one of these categories. Next thing we're going to do now is do the math side of this. We have to print out this statistic. So we're going to say if the null hypothesis is true, and our counts should have been closer to 340.25 on every one of these categories, how far is this table from all four of these expected counts? And in terms of how far it is, it's the chi-squared test statistic. We'll use this in the next chapter 22 as well. We take the difference between the count observed, the expected count, and we square that, divide by the expected count to get one so-called chi-square component. Add them all together. We have four components to compute, and that's going to be our test statistic, chi-squared. So that's going to be our next step. Let's throw this on the paper just for quick reference. Okay, I've got the formula below. I'm going to need the table as well, so let me bring this down. Here's the formula, here's the table, and we've got everything we need on screen. The expected counts, color-coded in green, are these values that fall into this part of the formula. The observed counts is what the study actually produced, so it's just this table we brought down below as well. So now here's what chi-squared is going to look like. Chi-squared is, let's take and compute on a step-by-step basis this component. Really expanded in this way, just four different terms. And because we're computing a test statistic, which we usually round to 4 decimal places, that's been our practice all semester long, I'll round these to 5 decimal places and do a final round on 4 places. So take the observed count for first category, 328 minus the expected count, that is the 340.25 here, squared, divide by 340.25, and that's our first component, 0.4404. Hang on, I don't think I got those digits in. 0.44104. Knew I was missing something. Okay, 1 down, 3 more to go. So again, all we're doing is tracking through that formula exactly as we see it on paper. Do it one more time, and this is what it would look like. And a good calculator, you can just do the last entry you put in. On this calculator, it's the up arrow. All you're changing is to the next observed count, 334. So on that next computation, it's small, but that's because it's pretty close to the expected count, 0.11481. And down the line we go. Kind of tedious to do this by hand, so we're going to show this in a different way on the next problem, how to make RStudio just do all this for us, if you're curious how that goes. But as far as doing this as a by hand math problem, you know it's really not that bad. So we're mainly just studying the formulas, seeing how they go on our first example. So redo it with 372. This one's way off from 340.25, but we don't know if it's off enough for significant statistical evidence. Here's the value we get, 2.96271. And last one, change to 327. And it's a 0.51598. So those are all the chi-square components. Let's give it that name in the notes. These terms are the chi-square components. Because chi-squared itself in blue is a test statistic, if we reject the null hypothesis, it means one of these is false. That doesn't give us a lot of information. It's an overall test, but a follow-up analysis can help us narrow down which one is false by looking at the chi-square component. The largest one is 2.96271, which belongs to the summer category. So if we in fact reject the null hypothesis, it's because of summer. higher incidence of homicide occurs on a percent basis for that region in that season. So now that we have the test statistic, we just have to put it all together. Let's actually add these together: 0.44, 104, 0.11, 481, 2.96271, finally plus 0.51598. So altogether, there's our test statistic, 4.0345. Let me double check the digits once again. Okay, I think I've got it in, and we did it. Now, every single time we've computed a test statistic, there was an observation that we made. Maybe we didn't make that observation every single time, but we've often emphasized it's a type of standard deviation. The distance in terms of standard errors, which is an approximate standard deviation, that the data is away from the value in the null hypothesis. But that's not true for chi-squared. This is a whole different kind of test statistic. All it's measuring is a distance from this table here, your actual observed counts, and a new table where all expected counts are 340.25. So getting something like 4, 7, 10, we can't celebrate at all. That's not like 4, 7, 10 standard deviations that the data is away from the null hypothesis. We now have to calculate the test statistic directly from the chi-square distribution. So that's our next step. Let's turn over to the next part of the notes. To get the p-value, we just have to follow this final process here. Before we delve into the p-value side, any questions at all, folks, on the test statistic portion? Okay, well, the p-value is just another RStudio operation, kind of like when we used p-norm or pt for the t-distribution. This time we're using p chi-squared. It's the chi-squared procedure, so that's got to make sense. Notice k minus 1 is critical there. Let's define that first. K minus 1 is the degrees of freedom, so let's say on paper, df refers to degrees of freedom often, and in this chapter it's no different. Formula here this time is k minus 1, a lot nicer than the chapter 20 formula. So we have to recall what was k. K was just the number of categories for your categorical variable. It's 4 in this problem, so we go back down here and just say it's 4 minus 1. Let's do a quick highlighting just to tie that concept together. If you have k is 4 here, then the degrees of freedom is k minus 1, 4, 3. And we don't come back to that until we're way down at the bottom, about to compute a p-value. So degrees of freedom are done. We just have to write out the R syntax. P-value is going to be p chi-squared. Now, every one of our hypotheses until this chapter had an idea of a left tail test, a right tail test, or a two tail test. But chi-squared, again, is different. They are always a right tail test. We are always putting in, no matter what the null is, our alternative is effectively always the same, and we're always setting lower dot tail false. So go your chi-squared value, 4.0345. So this plugs in here. Put in your degrees of freedom. Forgot to finish the thought there. That's 3. So this plugs in here for degrees of freedom. And then always, no matter what, set lower dot tail false. So that's the syntax from this. We have a p-value ready to output. And here it is, p chi-squared, 4.03. I'll go with our approximated value just to make it similar on paper here. Degrees of freedom 3, lower dot tail, false. And we've got a p-value. It's gigantic. Even though we had a 4 here, if that was a t-distribution, that would be statistically significant for almost any significance level alpha. But in chi-squared, it's not significant. it's 0.2578. This is much bigger than alpha. It looks like that's still on page. We set alpha to be 0.01. So that's greater than or equal to 0.01, which is equal to alpha. Actually, let me redo the color coding here. Usually for carry out the necessary computations, we want two things, the test statistic and the p-value. So I just want to emphasize those are the major things we're doing. And the next is just to guide us on the conclusion. That's greater than or equal to 0.01, which was our significance level alpha. So I want to just emphasize that's not part of the answer, just the p-value is the major end there. So we've got it. Our syntax was just copied from the formulas above. All we need to now give is a practical conclusion, which means we return to whatever our parameters were, whatever the null hypothesis and alternative are, and conclude based on that entire setup here. Before we make our conclusion, any questions or comments so far? Okay, well, the practical question of this problem was, is there some relationship between the seasons and incidence of homicide in this particular region? We said that more precisely when we wrote out our parameters and our null alternative hypothesis. But if your p-value comes out large, by large we mean anything that's equal to or larger than 0.01, then we still go back to this statement right here. But what we say this time is we failed to provide significant statistical evidence that this occurred. Let me actually box out the whole thing. So let's put that to words. Finally, we'll say, hang on, I did something with a font. Let me fix that. There we go. We're back to normal. Finally, we can say this study fails to provide significant statistical evidence and we're testing at the 1% significance level, at the 1% significance level, that, go back down to here, this is true, but using the context, using ordinary words. So we have to capture the essence of this, review what we said the parameters P1 through P4 were, true proportion of all homicides in this area that occur in the specific seasons, respectively. So we failed to provide significant statistical evidence that the true proportion of all, specifically homicides for violent crimes, homicides in this region is, let's say, different from we said proportion, so putting in a fraction is kind of weird. If you did, that's no harm done, but as a proportion, it would be 0.25. I think that just flows a little bit better in the wording. Is different from 0.25 for at least one. We can't say 1 I through 4. We have to say what those were. I is referring to P1 when I is 1, P2 when I is 2. But these were referring to the seasons, winter, spring, summer, and fall. So we can say for at least one of the seasons. And everyone knows there's 4 seasons. If you wrote out winter through fall, that'd be fine as well. That's more specific. If you made it a little bit more terse because we know what the 4 seasons are, you could end it right there. That conveys the same kind of information. We said at least one, and that's what this was conveying as well. We could have wrote here for at least one I as well, matching up if we really wanted to. So that's our conclusion there. And I want to leave this below as a screenshot just for the sake of reference. Let me emphasize that this is my answer. I guess a box is the universal way of saying my answer ends right here if you put a box on it. But this was the guide on getting to that answer. We failed to find evidence that this was true down below. Again, this is following the same process we've been doing all the way back since chapter 14, right around weeks 4 or 5. I think we were doing that content. It just feels different because our hypotheses look different, but match up what's similar with what we've been doing before, and you'll feel once you get through the initial weirdness of the new hypotheses, you're not doing anything too different. Actually, what made this problem a little bit more tedious is we did it 100% by hand, and you can do that for any problem you do on homework, any problem you do on the final exam. But the final exam is a take-home project, and the homework, RStudio is encouraged as well. So I want to show a problem like this in a different way, where we're going to heavily take advantage of RStudio next. Any last questions or thoughts at all, folks, with chi-squares so far? Okay, well, let's do it all over again. Here's another pretty realistic chi-squared scenario. This one is about blood types. And the thing tricky about blood types is if you're working with the, say, American Red Cross, they have some national values that are given for type O, A, B, AB. We're not focusing on anything more specialized, just those two types of blood, four types of factors here. But if you go to just a really specific region anywhere in the USA or maybe in a different country, those change. That's not universal everywhere in the USA. It's just a national average. And change the country, they can change here as well. So here's the context. A regional hospital is analyzing its blood bank reserves to ensure it is adequately prepared for emergencies. Nationally, American Red Cross reports distribution of blood types in the general USA population to be these values. Now, here's the next part of the context. The hospital's medical director suspects that the local donor population, so imagine we're maybe in Rigby or maybe somewhere in Colorado, who knows, but we're in a really specific town, and there could be something about the demographics of that town that tells us national values might be off by a little bit or maybe quite a bit, depending on that demographic set. So they suspect the local donor population might have a significantly different distribution due to regional demographic variations. To investigate this, the hospital's research team takes a simple random sample or 400 recent blood donations. Okay, so they have recent blood donations, probably somewhere there's a big database. They pulled in that database, N equals 400 donations. So that's our total sample size on this one. And once they looked into that, they observed the following distributions of blood types: 200 type O, 130 type A, 55 type B, and 15 type AB. Now we wonder, how well does that match these distributions? 50% of 400 would be 200. That's slightly less than 50%, and this is at 200. So you know they're close. This is 4%. This is at just 15 of the 400. It might actually fit pretty well, but we want to see, can we detect a statistically significant difference in these counts? So these are all from here to here, the observed counts. I guess that's a pretty big red flag when it said they observed, and here's the counts that they got. So we have one categorical variable, and the categories are just the 4 outcomes. What blood type occurred among the 400 blood donations in this region? So that puts us into chi-squared. We want to check at a 1% significance level if does the observed data provide sufficient evidence to conclude the local blood type distribution differs from the national distribution. These values given here from the blood from the red cross. Let's highlight that just for recollection on the overall question here so far. Any questions or comments at the moment? Okay, well, they in fact gave us 4 probabilities. So this problem flows a lot different than the last one we were just taking a look into. Let's go back up to the top here of this information page and setting up the hypotheses. We're in this general null hypothesis situation where we have a probability for every single one of the parameters given. First, let's write out what these values are. On the notes, we call them P1 naught, P2 naught, and so on. So let's put them on paper. P1 naught is 0.45. P2 naught, that's always awkward because that's a stacked subscript. The 0 is a subscript of the 2 that we wrote there. That's 0.40. P3 naught is 0.11. And P4 naught is 0.04. So that's the first element we have right here from this statement. We have the specific values. It better add to exactly 1. You know, that's not a bad thing to check. That's here to here, 0.85, 0.96. Yeah, that adds up to exactly 1. So we're on the right track. If that didn't work out, then it could be 2 approximation errors. So you should expect close to 1, like 0.99 or 0.101, something like that. But if it's way off, the problem is just inaccurate. Something's wrong with the question. So we're going to make this our null hypothesis. But before we dive to that step, we have to say what the actual parameters are in the very first place. So part A, describe the unknown parameters, is us putting on paper what is P1 through P4. That's the PK value. But this should feel pretty similar to what we did in the last problem. Unknown parameters with context would look like this. Let P1, P2, P3, P4 denote the true proportion of, in our chapters 19 and 20, we would have said proportion of successes, but we don't have that notion of success versus failures because there's 4 outcomes, type O, A, B, AB. So we have to say that here, true proportion of type A, B, AB, or hang on, I think I skipped one. Let me start with type O to keep the data in the same order. You definitely don't want to scramble things because that can mess up some of our work. Type O first, then A, B, AB, blood types, or I'll just leave it as type. Type A, B, O, A, B, A, B, among all. So here there are 4 outcomes corresponding to the 4 parameters. You also have to say what the population is. And we were looking into some specific region which had some interesting regional demographics. That's why they're doing this chi-squared procedure. So I'll just say, because the context didn't tell us further, a little bit more bluntly, among all people in this region. So that's our statement of parameters so far. Any questions or comments at the moment? Okay, let's keep on delving into this further. Now, just once again, for the reference on what we're about to write, what we put down on paper is we notated what the right-hand sides are, the PI naught values. Then we've notated and we said specifically what the parameters themselves are in blue. So now we put them all together, and that's our null hypothesis. Just join these in a corresponding way. So let's say test H naught, that P1 let me follow the color coding. P1 is equal to 0.45. P2 is equal to 0.40. P3 is equal to 0.11. P4 is equal to 0.04. That's a lot of writing for just a null hypothesis. But hey, we're halfway done. That's one hypothesis, and we're ready for the next. So again, once we say what the parameters are, join them with a hypothesized value. The null hypothesis is just hypothesizing there's no change. Even if we're in this specific region, it's the same as the national demographic with respect to blood types. So null hypothesis, statement of no difference, nothing's going on. We'll test that against an alternative hypothesis, HA, which is a statement that something is definitely happening in these data. At least one of these equations is false. So let's say it this way. In the prior problem, we were able to say Pi is not equal to 1/4 because we had one and only value for every parameter. That's a pretty convenient way to say it. But for this alternative hypothesis, here's a decent way to say it. Usually we like to say both null and alternative in terms of the parameter values, but sometimes ordinary words is a little bit better, and this is one of those situations. I'll say here for HA, at least, one equation in H naught is false. And again, we're not saying less than or greater than, we're just testing both directions, not equal. When we say at least one, it could be the first equation or the very last. But when we say at least one, we mean maybe it's two equations that are false, any two or three equations, or even all four equations are completely false for this region. And that's what the alternative is going to test. So it's a big statement, and we're going to test this at alpha equals 0.01. And this is the first time we've put down an entire hypothesis just purely using ordinary words. For citing the null, which is in terms of parameters, then it's still in a similar spirit of what we've done before. But again, chi-squared flows a little bit differently, so that's why this problem feels quite a bit different than those hypotheses. It's good to go really careful stating these first. Any questions at all, folks, getting them down on paper? Okay, next part of the process is saying, compute your expected counts, which would mean you have to take n is 400, multiply it by Pi naught. These are the Pi naughts, and that will give you your 4 expected counts. But like we mentioned, you can do that by hand, or you can take advantage of RStudio, and we'll try this out the RStudio way, just to give a variation on how to work these kind of problems. RStudio is very convenient because it feels a little bit less like busy work, more like just doing a normal computation, like say in chapter 19 with the t-distribution. First thing we have to put down is the observed counts. So let's go counts, gets, C to combine in a parenthesis, and definitely keep everything in the same exact order. Start with type O, 200, 130, 55, 15. So we have our counts. Let's double check those values. That looks about right. Once we get the counts in, we have to also put in the hypothesized probabilities. I'll call this prob for short. Prob gets C, 0.45, 0.40, 0.11, 0.04. So those are our first two levels of what we have to put inside. Then the procedure is chi-squared.test. But we are actually not going to run that procedure yet. We want the expected counts first. Chi-squared.test stores everything, expected counts, chi-squared components with a slight formula adjustment. So we're going to make another strange adjustment to our syntax, something we haven't quite done before. Instead of doing something like t.test or chi-squared.test, let's store it. I'm going to call this result gets the output of chi-squared dot test. So that one down below. In chi-squared dot test, follow the guidance. X is going to be the counts. And we skip Y, we skip correct equals true, go to this. And this is really actually kind of touchy. You have to write exactly as P equals prob. So the P equals part is the required portion there. Give it prob for probabilities, and that's going to store the chi-square test inside result. So let me double check how it's running. Let me hit Control A, Control Enter. Looks like we have everything. And what we want is the expected counts. So let me put in just a little notation here. Here, this is the expected counts. And how to get them, go to Result, $sign to select what you want. And notice there's a bunch of stuff. Statistic, parameter, p-value, method, data, observed. Observed is just the counts that we put in. Expected, that's what we wanted, the expected counts, if the null hypothesis is actually true. So go results, $sign to select one thing stored, the expected counts, run the whole thing, and there they are, 180, 160, 44, 16. Let me just write here in ordinary words, the expected counts. Are 180, 160, 44, 16. So what we're now saying is, if this null hypothesis right here is actually true, and you sampled at size 400, there should have been 180 type O people in this sample, 160 type A, and so on. Effectively, all it's really done is taken the sample size of 400. We want to check the first expected count 180, multiply times 0.45. That's where we're getting the 180. Multiply that's 400 by 0.40, you get the 160, and so on. This is just a little bit more convenient way to do it. And it becomes wildly convenient when we look into chi-squared for two-way tables in the next chapter. So up to you if you'd like to use this trick. I'll share the syntax here. It's actually not too much to write up. Next thing we're going to check is if the data meets the condition for chi-square itself. Well, any questions so far, folks? Getting those 4 expected counts? Okay, well, as far as the conditions go, we are really just checking 2 things. Let's pull this up for reference. We want to double check that we have a random sample from the population of interest, and these 2 parts are telling us if our sample size is large enough. Notice our expected counts are pretty high. They're at minimum 16. So this part 2 is true. No more than 20% of the expected counts are less than 5. Absolutely true. If the minimum is 16, all individual expected counts are 1 or greater. Absolutely true as well. But if this was, say, 3, then 25% of the 4 expected counts would have been less than 5, and the whole condition fails right at that step. So our sample size was actually getting kind of close to being not large enough, even at a sample size of 400. If that percentage was smaller, way smaller, then this might have needed to be 4,000 or something along those lines. But really, the first condition we should address is randomization. But let's think about this really carefully. It did say a simple random sample was taken of blood donations, but these are people who donated to the blood bank. the population is everyone in this region. So now we have to ask ourselves, does everyone in this region donate at the blood bank? Or maybe a larger question is, does the type of blood depend on if the person is the type of person to donate blood to the American Red Cross, for example? Those are some pretty large questions that you might imagine. And I personally would say there is a particular individual who does donate blood. They might have specific opinions on a lot of different things, but I bet you their blood distribution has nothing to do with it. So I would say, even though this is specifically people who donated blood, probably still a representative sample of everyone in the region if we're talking about blood types. If we're talking about political affiliations, that could actually be different. So you have to be pretty careful with this kind of problem. But I think in this case, we're probably okay. Let's say for part one, the sample is a simple, random sample, but it was exclusively people at the blood bank, which causes us concern. But I'll put here further, moreover, people donating blood to a blood bank is representative of the entire population with respect to blood types. Again, that may or may not be true. So that's something that we might want to think about a little bit harder for doing this kind of study. But I would say it is a reasonable assumption to say that type AB is just not a person who's more likely to not donate to the blood bank. That's why it's so low in the count. I would say blood type has nothing to do with the type of person who donates to blood banks on a regular basis. So in my opinion, again, this might need further research, further analysis. I would say we have a simple random sample, and it is representative of all people in this particular region. And then as far as condition two, we can just say briefly, the minimum expected count is 16, which is greater than or equal to 5. And so the sample size is large enough. So overall then, the conditions are met. The conditions are met overall. So we're in pretty good shape with these data. Any last questions or thoughts, folks, thinking about the conditions themselves? Okay, we're in fact just nearly done with this problem. So let's see what happens next on the analysis. Next, we want the chi-squared value, the p-value for the test. We can find the distance between the observed, expected, square it, divide by the expected count 4 ways, get the test statistic like we did before. But if everything is already here, this is all you need to do. So I'll call this part test statistic and p-value. Here, we just need to say result, or you could just run chi-square.test again if you prefer. That would work out just fine. So rerun this. When result occurs, it just outputs the chi-square test that got stored. It gives us right away, chi-square test statistic is 10.66. So let's write that in. Chi-squared is 10.66. P-value, or right here, just as a reminder, there's 4 outcomes for K, so the degrees of freedom should be 3, as this indicates. Then next, the p-value, is actually large, which is kind of interesting on this problem. P-value is 0.0137. Ordinarily, that looks like a small p-value. And when I was doing this problem this morning just for practice, I was a little bit upset that I threw this at 1% because this is two problems in a row that are not significant. But those are just as important analyses as the significant problems. But what I didn't do is change the 1% significance level, because once again, that's an unethical thing to do. And even changing it on the notes is probably a bad practice as well. So we're going to stick with this 1% because it was baked into the notes. That would be a bad revision. That p-value then is larger than, greater than or equal to 0.01, which is alpha. So two in a row, not significant. Our next chapter notes will have a significant result for our next chi-squared procedures. So once that's done, the last thing for us to do is just give the practical interpretation. To do that, let me drop in our parameters, our hypotheses. Let's also drop in part of the context up here, the information about the National American Red Cross blood distributions. I'll leave this down below just as a reference if you come back here to see how we put everything together for our practical conclusion. We can now say, first, let me just do this in kind of a parallel way to the last problem. We are going to retarget this. Or we're just going to simply say the study does not have significant statistical evidence in favor of that. So let's write this out. These data do not provide significant statistical evidence at the 1% significance level that. Then we come back here, at least one equation and H naught is false, but we can't say that. We have to use the context. So we go here. We didn't have evidence that at least one of these equations is false. But then we have to say what P1 is. So we're going to really start here. That the true proportion of type O, A, B, AB among all people in this region now we can say is different than one of these values at least. Or we can just cite the National American Red Cross information here. If we did that, it's a little bit faster to say, but I'll leave it up to you as a judgment call, how you would like to say it. So I'll say here that at least, let me double check the flow of this, that the true proportion of those donations among all people in this region, let me say this a little bit differently, is different than, and fix my penmanship, is different than the values, and let me say more specifically, the values are proportions provided by the American Red Cross for at least one blood type. So we have to get that at least one statement in there somewhere. And we said at least one blood type to match up that part right there in the alternative hypothesis. It's a tricky statement to put together because we're jumping through different levels. We have no evidence that the HA is true, but it's written in terms of the null. We have to say what our parameters were at the same time. And you could say at least one, P1 is not equal to 0.45, type O is not equal to 0.45, type A is not equal to 0.40, and so on. But I paraphrase a little bit by just citing the National American Red Cross values, which is providing that same exact information. So let me complete the color coding on how we put those together. So all color coding above and below correspond with each other, and that's how we put down the conclusion for this particular type of chi-square. We did it, folks. That's chi-squared in a nutshell. We're not completely done with chi-square. We're going to look into it in a new context where there's now two categorical variables all at the same time. But you know, as far as that goes, it's really, really very similar. Another thing that's kind of interesting about this is we got so close to rejecting the null hypothesis, but we didn't quite get it. If this was at 5%, we would have rejected the null hypothesis, and we might have wondered, why was the null hypothesis rejected? And this is how you can check. We'll look into this further on our next chapter 22. So think of this as a preview, the so-called chi-square components. What we're computing with the chi-square components is the individual terms that we see here. The output on their code gave us the test statistic, but it just glommed all the components together. Sometimes you actually want to analyze these, especially if you reject the null hypothesis, like we'll do in chapter 22. So we'll borrow this syntax again, and here's what it's going to look like. For the chi-square components, go to result. We're going to select one particular output, the residuals. If you raise the residuals to the power of 2, it becomes exactly the chi-square components. So run that, and here are those components. If you add up all 5 of these numbers together, you get to 10.66. And now, if we rejected the null hypothesis, say that it was below 0.01, then it would tell us the major reason we have rejected the null hypothesis is because of the second component, which would mean that's because P2 equals 0.40. That was the most false equation. The count for that was the most off in our data. So this helps us narrow down in the overall test what the particular conclusions would be on why we rejected. So once again, we'll look into this all even more in the next chapter notes. But for the moment, let me park this right here. If you like seeing this method for chapter 21, the syntax is pretty short. Here's what it looks like. And I would encourage you when you do the homework assignment for this section, give this a try in at least one of the 2 problems there. Mainly because when we go to chapter 22, doing it by hand is exceedingly painful. There is a lot of computations, but it's just about the same exact amount of syntax other than importing the data. We'll look into how that goes. So we're going to take advantage of RStudio a lot more in chapter 22, so we're not so heavily bogged down on all the computations of expected counts. But we did it. Now when we take a look into our next chapter, chapter 22, here's what it's going to look like. At first, it looks pretty similar if you scroll down to this block right here. We have very common information about expected counts. We have a chi-square test statistic. We have a p-value based on p chi-squared just like before. But something is very different. Our chapter 22 test is a hypothesis test, very, very unlike anything we've ever done before. This is not a test on the parameters. This is a test on the categorical variables themselves. We're going to test, are the 2 categorical variables provided independent or dependent? Independent in the statistical sense, and Using rules of independence from probability theory, it provides us with this new formula for the expected count. Again, a lot of expected counts have to be computed, even in smaller questions like these. These are not large two-way tables, but this is a painful problem to get through. So we'll show how all this goes, how to put together the null alternative, very different kind of hypotheses because they're about the variables themselves on both of them. But after we get through the newness of this, it'll feel like a really strong review of what we did in chapter 21. So rather than trying to push through the problem and talk about the notes too much on the last 4 minutes and some change on Wednesday, I think this spot right here will be a good stopping point for us. We'll return to chapter 22 next week. It's not a long chapter, so we'll also be starting the ANOVA method, chapter 24, our final chapter of the semester. Well, any last questions, thoughts, or comments at all, folks, before we call it a day? Okay, well, have a great weekend, everyone. I'll be trying to finish up grading on the exam on Friday. It could go a little bit later, but my hope is to have exam one fully graded, returned back to everyone sometime Friday afternoon. But have a great weekend. I'll see you all next class.